The first challenge is lift. To leave the ground vertically, the aircraft's propulsion system has to generate enough upward force to overcome its weight. Unlike a conventional airplane, it can't depend on forward speed and a runway during takeoff. So what actually creates that upward force? Electric motors drive the propellers, turning electrical energy into mechanical rotation and then thrust. By controlling those propulsion units, the aircraft can generate the upward force needed to lift off and remain stable in the air. But why use several propulsion units instead of one giant rotor? Many eVTOL designs distribute propulsion across multiple motors and propellers. That can give engineers more control over the aircraft and provide redundancy while spreading propulsion across the airframe. But generating lift isn't enough. The aircraft also has to stay balanced. By changing propulsion output across different units, its control system can adjust pitch, roll and yaw, allowing the aircraft to hover, turn and remain stable. But how does the aircraft know when to make those corrections? Sensors continuously measure things like motion and orientation. A flight control computer processes that information and sends commands to the aircraft's propulsion and control systems again and again in real time. But hovering is only half the challenge. Now the aircraft has to accelerate forward and transition from primarily vertical lift toward efficient forward flight. This is one of the most critical phases of the entire journey. As the aircraft gains forward speed, the wings begin generating more aerodynamic lift. That means the aircraft no longer depends as heavily on vertical propulsion to support its weight. During cruise, the wings can do much of that work. So think of the aircraft as a balance between two forces. Lift acts upward to keep it airborne, while thrust moves it forward. During cruise, the wings provide aerodynamic lift, and the propulsion system provides the forward push. Once the transition is complete, the aircraft can settle into forward cruise. Its wings generate aerodynamic lift, while the propulsion system provides thrust. The flight computer continuously manages the aircraft as it travels toward its destination. But there's a catch. Every kilometer of flight uses energy. An eVTOL has to carry its battery through the entire journey. So reducing drag and using energy efficiently can make a major difference to how useful the aircraft becomes. And batteries aren't the only thing affecting efficiency. As the aircraft moves forward, the air pushes back against it. This resistance is called drag. Engineers shape the aircraft and wings to reduce drag, helping the eVTOL use its energy more efficiently. But what happens when the aircraft needs to change direction? Its flight control system coordinates the aircraft's attitude, propulsion and aerodynamic surfaces, allowing it to bank and follow a new flight path smoothly. But the journey isn't over. To land at a rooftop vertiport, the aircraft has to reverse the process. It slows down, transitions away from efficient forward flight, and prepares to generate the vertical thrust needed for a controlled landing. Now the aircraft is back in vertical flight. It aligns itself with the landing area, reduces its horizontal movement, and carefully controls its descent. The goal is simple: arrive precisely where the vertiport is designed to receive it. And this is where precision matters most. A rooftop landing requires the aircraft to maintain its position while dealing with wind, changing conditions, and a limited landing area. Its sensors and flight control systems must continuously monitor the approach and keep the aircraft centered. And finally, the aircraft reduces its vertical lift and settles onto the landing pad. In just one journey, we've seen the complete cycle: vertical takeoff, forward flight, controlled transition, and vertical landing.